Welcome to our channel. Today we're diving into the cosmos to uncover some of the strangest scientific facts about the universe. From black holes that defy the laws of physics to the mind-boggling concept of time dilation, get ready to have your mind blown. We'll delve into the bizarre world of quantum entanglement, where particles are connected across vast distances in ways that challenge our understanding of reality. So buckle up and get ready for a wild ride through the cosmos as we explore 10 mind-blowing scientific facts that will leave you questioning everything you thought you knew about the universe. Imagine a place where gravity is so strong, so utterly dominant, that nothing, not even light, can escape its grasp. These are black holes, cosmic abysses formed from the death throes of massive stars. Picture a star, many times the mass of our sun, collapsing in on itself. As it shrinks, its gravity intensifies, pulling everything in its vicinity toward an inescapable point. The boundary beyond which nothing can return is called the event horizon, a point of no return. Cross it, and you're lost forever to the black hole's insatiable appetite. But don't think of black holes as mere cosmic vacuum cleaners. They're engines of creation and destruction on a grand scale. As matter spirals into a black hole, it heats up, emitting intense radiation that can be detected across billions of light years. Some black holes, known as quasars, are among the brightest objects in the universe, outshining entire galaxies. But their brilliance comes at a cost, as they devour everything in their path. Black holes challenge our understanding of space, time, and gravity itself. If black holes are the ultimate cosmic graveyards, then neutron stars are their ultra-dense tombstones. Imagine a star more massive than our sun compressed into a sphere the size of a city. That's a neutron star, the leftover core of a supernova explosion. These stellar corpses are some of the densest objects in the universe. A teaspoonful of neutron star material would weigh billions of tons on Earth. Neutron stars spin rapidly, some making hundreds of revolutions per second. As they rotate, they emit beams of radiation that sweep across the sky like cosmic lighthouses. We call these pulsars, and they're some of the most precise timekeepers in the universe. But don't let their small size fool you. Neutron stars are incredibly powerful. Their magnetic fields are trillions of times stronger than Earth's, capable of distorting the very fabric of space-time. In the vast expanse of the cosmos, there's a speed limit that governs everything: the speed of light. This fundamental constant, approximately 299,792 kilometers per second, is the ultimate speed limit of the universe. Nothing, not even information, can travel faster than light. Light travels so fast that it could circle the Earth over 7 times in just 1 second. That means that when you look at the moon, you're seeing it as it was a little over a second ago. But the speed of light isn't just about how fast photons travel through space. It's woven into the very fabric of space-time, affecting how we perceive time and distance. As objects approach the speed of light, time slows down for them relative to observers at rest. This phenomenon, known as time dilation, is one of the strangest predictions of Einstein's theory of special relativity. Our universe is a strange and mysterious place filled with wonders that we're only beginning to understand. And perhaps one of the biggest mysteries of all is dark matter, an invisible substance that makes up a whopping 85% of the matter in the universe. We can't see dark matter directly. It doesn't emit, absorb, or reflect light. So how do we even know it's there? We infer its existence through its gravitational effects on visible matter, like stars and galaxies. Imagine watching a merry-go-round spinning at a leisurely pace. Suddenly its speed increases dramatically, as if an invisible force is pushing it along. That's similar to how dark matter affects galaxies. It provides the extra gravity needed to hold them together, preventing them from flying apart. Scientists believe that dark matter is made up of exotic particles, unlike anything we've ever observed. Imagine looking up at the night sky and seeing a faint glow, a whisper of light coming from every direction. That's the cosmic microwave background radiation, the afterglow of the Big Bang, the event that birthed our universe over 13.8 billion years ago. Think of it as a baby picture of the universe, a snapshot of what it looked like just 380,000 years after the Big Bang. Back then, the universe was a hot, dense soup of protons, neutrons, and electrons bathed in a sea of radiation. As the universe expanded and cooled, this radiation stretched and faded, eventually shifting into the microwave part of the electromagnetic spectrum. Today we can detect this faint afterglow with specialized telescopes, providing us with a glimpse into the universe's earliest moments. The cosmic microwave background radiation is remarkably uniform, with only tiny temperature fluctuations. The quantum world is a strange and counterintuitive place where particles can exist in multiple states at once, and where information seems to travel faster than light. And perhaps one of the most bizarre phenomena in quantum mechanics is entanglement, a phenomenon that even Einstein called spooky action at a distance. Imagine two particles, linked together in such a way that they share the same fate, no matter how far apart they are. You measure the state of one particle, and instantly you know the state of the other, even if they're light years away. It's as if these particles are connected by an invisible thread, communicating with each other instantaneously, defying the limits of space and time. Some physicists believe that entanglement could be the key to understanding the fundamental nature of reality, suggesting that the universe is interconnected in ways we never imagined. Our universe is not static, it's dynamic, constantly evolving and expanding. It's like a balloon being inflated, with galaxies moving further apart from each other over time. This expansion was first observed in the 1920s by astronomer Edwin Hubble, who noticed that distant galaxies were moving away from us at speeds proportional to their distance. But here's the kicker: the universe's expansion isn't slowing down, it's accelerating. This discovery, made in the late 1990s, came as a complete surprise to cosmologists. It means that there's something out there, something we can't see or interact with directly, that's pushing everything apart. We call this mysterious force dark energy, and it's thought to make up about 70% of the total energy density of the universe. Its nature and origin remain one of the biggest unsolved mysteries in modern physics. Time, the relentless march of moments, seems like a universal constant, ticking away at the same rate for everyone. But according to Einstein's theory of relativity, time is not absolute, it's relative, depending on your motion and the strength of the gravitational field you're in. Imagine two identical clocks, one stationary on Earth, and the other traveling at a significant fraction of the speed of light. As the moving clock approaches the speed of light, time slows down for it relative to the stationary clock. This phenomenon is known as time dilation. It's not just science fiction. Time dilation has been experimentally verified numerous times. For example, atomic clocks flown on airplanes tick slightly slower than those on the ground, albeit by a tiny fraction of a second. But the effects of time dilation become more pronounced at speeds closer to the speed of light. Our universe is vast, stretching out for billions of light years in every direction. But what if our universe isn't the only one? What if it's just one of countless universes, each with its own unique properties and laws of physics? This is the mind-boggling idea behind the multiverse theory. The multiverse theory is still highly speculative, but it's supported by several different areas of physics, including cosmology, string theory, and quantum mechanics. For example, the inflationary theory suggests that our universe is just one bubble in a much larger multiverse. String theory also predicts the existence of extra dimensions beyond the three spatial dimensions and one time dimension we experience. The Big Bang Theory is the prevailing cosmological model for the universe, describing its origin and evolution from a state of extreme density and temperature around 13.8 billion years ago. It's not an explosion in the traditional sense, but rather an expansion of space and time itself. Imagine the entire observable universe, everything we see today, compressed into a volume smaller than an atom. That's the singularity, the point from which the Big Bang is thought to have originated. In the first fraction of a second after the Big Bang, the universe underwent a period of rapid expansion known as inflation, growing exponentially in size. As the universe expanded and cooled, fundamental forces separated and elementary particles formed. Over millions of years, gravity drew these particles together to form the first stars and galaxies. Thanks for watching. If you enjoyed this journey through the cosmos, don't forget to like, subscribe, and hit the bell icon for more fascinating videos. The universe is a vast and mysterious place, filled with wonders that we're only beginning to understand. From black holes to the Big Bang, From quantum entanglement to the multiverse, there's always something new to discover. So keep exploring, keep questioning, and keep your sense of wonder alive.